In sections 5 and 6, we're going to look at the idea of solubility and solutions. So we've been talking about aqueous solutions, and we have talked about the state of having it as AQ. That's the terminology for a compound specifically which is dissolved in water. So we know that if we put a substance in liquid and it dissolves and seems to disappear, we call that soluble. Things such as table salt, sugar, anything that appears to go away when we put it in solution. If we put something such as sand into water and it just sinks to the bottom and it sits there as a solid, we deem that as insoluble. Now, this can be any material put into any other material as far as soluble or insoluble. We can be talking about gases in liquid, gas in gas, liquid in liquid, solid in liquid. Solutions can be any of those. But if we are talking about putting something into water specifically and it dissolves and creates a homogeneous mixture, this is what we define as an aqueous solution. And that's what we want to focus on in these sections. So when we're looking at an aqueous solution, we could have something such as table sugar. If you're making a glass of sweet tea, you put sugar in there. The sugar dissolves, and what happens is the molecules of sugar separate one from the other, and then you have these molecules of sugar floating around in solution. That is dissolving. But what if we put, instead of a molecular compound, we put an ionic compound, an ionic solid, into water? Well, some of them dissolve and some of them don't, but when you have an ionic compound that dissolves in water, what it will do, in addition to dissolving, it will do something called dissociate. And that just means it breaks apart into the individual component ions that you have in that compound. Here's a representation of what you would see. So if we take NaCl as a formula unit, so we've got little crystals of table salt, and we put them into water, what's going to happen is we don't have any longer attached formula units of sodium and chlorine bound together in there. The water molecules are going to surround these ions, such as the sodiums or the chlorides, and they're going to draw them away from one another. And that has to do with the properties of water that we'll talk about in other chapters. But basically what it does is it allows the ions, the sodium ions and the chloride ions in table salt, to act as free ion agents. Right, now when that happens, when you get a substance that completely dissociates, completely dissociates into ions in water, this is what is called a strong electrolyte. And you can imagine a strong electrolyte has lots of ions. You can also have weak electrolytes in which some of the material dissolves into ions or dissociates into ions, and some of it remains in the formula unit form. And then you can have non-electrolytes, such as table sugar, where you put it into the water, molecules come apart, but they don't create any ions. Okay, so strong electrolytes are going to be conductors of electricity because of the charge on the ions. So when we look at this, if we were to take a setup, and this is a demo we very often do in a seated class, if you take a standard light bulb and you hook it up to a battery, you've got a power source of some kind, and then you have leads that you can put into a solution. If I were to put the two leads into the water, the idea is that I need something to act as a bridge between those two leads to complete the circuit and get electricity flowing through that circuit. Well, if I put it in pure water, I have nothing but molecules of H2O in pure water. There's no ion there to carry a charge, so nothing's going to happen. Now, if I take that same setup and I put it into a sodium chloride solution, table salt, so salt water, I now have ions, positives and negatives, that can act to carry the charge across the leads and create a circuit. And when I create the circuit and complete that, then I will see the light bulb start to glow. If I have a strong electrolyte solution, the light bulb will glow strongly. If I have a weak electrolyte solution, it will glow, but not as strong. It will be kind of a weak glow. And if I have something like pure water, which is a non-electrolyte, okay, that will not light the bulb at all. Right? So we have strong electrolytes, weak and non-electrolytes. Here's an example of another strong electrolyte, silver nitrate. We put that into water. So when silver nitrate is in water, we no longer have silver nitrate units. We don't see silver and nitrate stay together. Instead, they dissociate. So we get silver ions that we see, and then we get the nitrate. These all are going to be able to conduct or carry an electrical charge. Okay, so AgNO3 would be a strong electrolyte. Now notice on this one, a little bit different from sodium chloride, we got the silver ions and then we got these polyatomic nitrate ions, but notice the nitrate breaks up just into the nitrate ion. It doesn't keep breaking down into nitrogen and oxygen. All right, so be aware, polyatomic ions dissolve as an intact unit, and that's a little bit different from molecular compounds that don't dissolve and don't carry a charge. It stays as an intact unit, the nitrate does, but it still carries a charge, so it can still act as an electrolyte. Now, we can have compounds, as we said, that are non-electrolytes, and then we can have compounds that just don't dissolve at all. And silver chloride is one of these compounds. Silver chloride doesn't do anything when you put it in water. We pour it in, it falls to the bottom. Now they're showing it here in sort of a cubic form, but it's just going to fall as a pile of powder in the bottom of the water. It's not going to break apart into independent ions. They remain, the silver and chloride ions remain bound to one another within this system, and so there's nothing to carry a charge here. So nothing but solid and water. I could easily pour the water off, dry the silver chloride, and I've recovered the original material. So what we want to look at is, what are the rules that govern solubility? How do we know that sodium chloride and sodium nitrate are going to be soluble in water, but sodium chloride does not? So if we're looking at any particular compound, a compound will be soluble in a particular liquid if it dissolves in the liquid. It's insoluble if it doesn't dissolve in the liquid. We've already made that statement. Okay. And in order to know what they're going to do, we have applied what we call empirical rules. Now, what do we mean by empirical rules? Well, these are based on experimentation. Okay, someone had to conduct experiments to see what is going to dissolve, what isn't going to dissolve. They looked for patterns in that, and then we've used that to establish our solubility rules. They're based on empirical data, on observations that have been made. Now, you may have seen tables of solubility rules. Those are certainly out there. We're going to present it in our flowchart form here. And we can get a table, we can create that, but let's look at it this way. So let's start with compounds that tend to be soluble for the most part. So when we say mostly soluble, we want to look at things that have a tendency to be soluble. That doesn't mean, well, it mostly dissolves and a little bit's left over necessarily. All right, let's look at this first block over here. We have compounds that contain lithium ions, sodium ions, potassium ions, ammonium ions, nitrate ions, or acetate ions. Those tend to be soluble. Right? Those, it doesn't matter what anion you put them with if they're a cation, or what cation you put them with if they're an anion. If you have those particular ions, those are going to dissolve in solution. Now, it may seem like, oh boy, here's a bunch more stuff to memorize, but a little bit easier if you look at the first three. You'll notice that they have something in common. Those are all group 1A compounds. Okay, the compounds in group 1A are almost always soluble. There are very, very few exceptions. Anything you're going to see in here, if it is a group 1A compound, it's soluble. If it's got ammonium nitrate or acetate, it's soluble. Also, if we take a look at these three in the next block over here, if it contains chloride, bromide, or iodide, usually soluble, but with some exceptions. So if it contains chloride, bromide, or iodide, then you need to look at what the cation is. All right, so there are three things you have to watch for. Is it silver, mercury, or lead? If you have silver, mercury, or lead with any of these, and notice these are all group 7A compounds, right? So if it's one of those three, then you're going to go this way, and it's insoluble. So those are the three exceptions. Otherwise, any other cation you put it with, if you put it with sodium, or you put it with calcium, or you put it with, and let me put the charges in there, if you put sodium, calcium, if you have it with copper, any of those, then it's going to be soluble. Those are going to dissolve when you put them in water. And then compounds which contain sulfate. Again, with a few exceptions, sulfate-containing compounds tend to be soluble. The exceptions are calcium, strontium, barium, or lead. And notice it's a little bit different from the list we had for the group 7As. All right, so if you have one of those four cations with sulfate, then it is insoluble. Otherwise, everything else is going to be soluble. And we'll present this later as a list, not in this presentation, but on the Blackboard site. We'll have a list of general solubility rules that you can look at and use to determine if a compound is going to dissolve or not. All right, so let's look at some examples of mostly soluble compounds. So we said that anything containing the lithium ion is going to be soluble. Okay, lithium ion is that group 1A. So if I had something like lithium bromide, lithium hydroxide, lithium carbonate, and notice there's a problem with this formula right here. That should be a 2 because carbonate is 2-, so sorry, that was a typo in there. Okay, and if you want, you can put that in so you can see the polyatomic on the hydroxide, but you don't need it there. So if I had any of those compounds, those are going to dissolve in water, and they're going to form strong electrolytes. I'm going to get ions out of those. All right, so that's case number 1. Now let's look at another one, case number 2. Let's say that we had a nitrate ion. Well, we've said that nitrate ions tend to be soluble. Again, doesn't matter what I put it with. If I had it with silver, lead, calcium, okay, and again, I need 2 of those, and I need 2 of those. Lots of typos, sorry about that. Those compounds all all dissolve in water, and they're going to form strong electrolytes. Those are all going to be ions in solution. All right, what if I have the other side of the coin here? Compounds that are mostly insoluble. All right, so what we're looking at, compounds that contain hydroxide generally tend to be insoluble unless we've got things like lithium, potassium, sodium, ammonium. We already said those things are soluble. So if I have any of those things that I already said were soluble in the first slide, they're still soluble. Anything else? Nope. All right, so now let's see, does it contain calcium, strontium, or barium with hydroxide? If I have one of those 3 ions, yeah, it's slightly soluble. Okay, so when we say slightly soluble, that means we can put it in water and a little bit will dissolve, but it probably won't all dissolve. It depends on how much water and how much solid you put in there, but chances are, no matter how much you put in there, you're going to have some solid left over. Okay, slightly soluble. Otherwise, if it's not one of the 3 listed here or one of the 4 listed here, it is going to be insoluble. So most hydroxides are going to not dissolve in water. Okay, sulfide, the sulfide ion. Most of those, with the exceptions we already mentioned, if I have any of these ions I already talked about that tend to be soluble, okay, those are soluble. If it's any other ion, then sulfides tend to be insoluble. And then compounds that contain the polyatomic ions carbonate or phosphate. Again, we go back to the ones we already said. Does it contain any of those cations? Those are always soluble. Okay, if it has one of those, yep, it's soluble, doesn't matter what you put it with. Otherwise, anything else, calcium, magnesium, iron, any of those, it's going to be insoluble. All right, so eventually you'll need to know some of the more common compounds. It's good to know that those group 1A, lithium, sodium, potassium, ammonium, good to know those are always soluble. Good to know that nitrates are always soluble, things like that. But otherwise, at this point, it's more important for you to know how to read this flowchart and use that to interpret solubility or insolubility than it is to memorize these flowcharts. Don't try to memorize the flowcharts, but do learn how to use them. And do know the more common rules, as I said, the things that are soluble, that are always soluble. Lithium, sodium, potassium, ammonium, nitrate, acetate, those kind of things are the ones we want to focus on. All right, so here's some examples of mostly insoluble. So we stated that carbonate ions tend to be insoluble. All right, so things like calcium carbonate, iron carbonate, strontium carbonate, copper carbonate, I can put those in water. Those are not going to dissolve. Okay, now note that solubility rules contain many exceptions. So this is why it's good to know the ones that hold as general rules, but don't try to keep that as an absolute all the time. So, you know, one set of rules supersedes another. For example, you know, carbonates tend to be insoluble, but these are always soluble. That rule came first. If that rule comes first, then we apply it first. So if one rule, if the cation says it's soluble, the anion says insoluble, which rule came first? The cation rule came first, we apply that one. So lithium carbonate, sodium carbonate, potassium carbonate, and ammonium carbonate are all soluble. Calcium carbonate, magnesium carbonate, silver carbonate are not soluble. All right, so here's the list. I apologize. I thought it was going to not be in here, but here it is. So we got it in here. And here's the general list. So here are the solubility rules, the ones that are mostly soluble. And then here's the list of exceptions over here. Note that those two have none. Here's your insolubles. And then here's all your exceptions down here. Note again that you will apply these rules from the top down. So the higher a rule is on this chart, the more precedence that it has. So whichever rule is higher on the chart, that's the one you follow for a set of anions and cations. And this may seem confusing, but as you start working problems and looking at it, you'll get a feel for what's going on with these, which ones dissolve and which ones don't. All right, so now that we know that we have things that dissolve in solution, now let's look at what happens when we take those things that are in solution and put them together with things that would not be soluble. So for example, sodium carbonate, Na2CO3. That is a common additive or a common compound in laundry detergent. And we've talked a little bit about the fact that it reacts with magnesium and calcium ions and precipitates from solution. All right, so what's happening is we said that anything that contains sodium is going to dissolve in water and it's going to dissociate. So what happens is I end up with 2 sodium 1 plus ions in the water, and I end up with a carbonate 2 minus ion. Sodium carbonate in water exists as ions, but now when I put that sodium carbonate into water that already contains magnesium or calcium ions, those 2 ions can react with the carbonate, which is free in solution. And those things, remember, according to the solubility rules, carbonates tend to be insoluble. Magnesium and calcium are not exceptions to the rule, so magnesium carbonate, calcium carbonate are insoluble in solution, and they will come together and precipitate out. Okay, so that's a precipitation reaction. When I mix 2 aqueous solutions, I end up with a solid. That's precipitation. We're going to start looking at different types of reactions here. All right, so here's a visual of a precipitation reaction. So if I were to take potassium iodide, which is a clear solution, a little bit hard to tell, but here's a pipette tip that they've got in here. The solution's in here. It's perfectly clear, just like water. And here was some lead nitrate solution that you see on either side of this yellow. It is also clear like water. When I mix those together, okay, so if I look up here, I started with potassium iodide and lead nitrate. Well, when I look at my rules, okay, potassium is a group 1A, so that one is going to be aqueous in solution. That's why I've put the AQ here. I'm going to have potassium ions and iodide ions. Lead nitrate, nitrates are always soluble, so I have lead ions and nitrate ions. Okay. Potassium and nitrate, always soluble, so I can write them together, but they're not really together. They're just ions in the solution. But now, when I put these two together, lead compounds tend to be insoluble. So remember, we looked at our chloride, iodide, bromide. They tend to be soluble with exceptions. One of the exceptions is lead. So when you mix them together, we form lead iodide, which appears as a bright yellow solid. Now, when we say a solid, sometimes people expect there to actually be like a chunk of solid that just immediately falls to the bottom. It's more likely to be just this cloudiness that we're seeing here. So the precipitate forms sometimes a color, sometimes white, but it will form some sort of material that makes the solution opaque. You can't see through it anymore. And if you give it enough time, eventually all of that solid will settle out to the bottom, and you'll have a layer of clear liquid on top and a layer of this solid on the bottom of the container. That's evidence of a precipitation reaction. Now, that doesn't always occur. We need to, again, use solubility rules to be able to predict whether or not anything would happen. So, for example, if we take potassium iodide, which is aqueous in solution, and sodium chloride, and put them in solution, theoretically, I could now rearrange the ions, and I can kind of partner swap here. I could try to put the sodium with the iodide, I could put the potassium with the chloride, but when I do that, sodium iodide, sodium is always aqueous in solution, potassium chloride, potassium's always aqueous in solution. So nothing happens. There's no reaction on this one. Nothing that is insoluble in solution. So this is why it's important to be able to use that chart and figure out those solubility rules. We can predict whether or not a precipitation will take place. All right, only insoluble compounds are going to form precipitates. That is key to predicting these precipitation reactions. So what we're going to do is look at the two solutions that were given that are going to have to contain soluble compounds. So the two things on the reactant side will have to be aqueous. So I have something that's aqueous plus something that's aqueous. Okay, and if I have a precipitation, two things will come together to form a solid. The other two things that were in there remain aqueous. So that's the phase pattern that you'll see for a precipitation reaction. Something aqueous plus something aqueous yields something solid plus something aqueous. All right, let's look at some examples of that. If we were to take potassium iodide and mix it with lead nitrate. So before mixing, we've got potassium iodide, so potassium ions and iodide ions. That one's soluble in solution, free ions. And then we've got our lead nitrate, so breaks apart into lead ions, or one lead ion and two of the nitrate ions. We're representing it just on a 1 mole basis here. Okay, so notice our balanced equation, that's what we're basing it on. So we started with 2 KIs, 2K, 2I, 1 lead nitrate, which has 1 lead, and then the 2 nitrates in it. Right, so here's our visual representation. We have them in 2 containers, nothing but ions. They're going to look like 2 containers of water in reality. All right, and then we're going to mix them together. When we do, the instant we mix the solution, all 4 ions are present in the solution. And so there was our aqueous and our aqueous. And now those ions are free to rearrange themselves. So now our lead, instead of seeking out nitrate, can seek out an iodide and form a solid. Okay, so those are going to precipitate out as a solid. And I'm going to have nitrates. Those aren't going to really do anything. I'm going to have these 2 potassiums that aren't going to do anything. And I'm actually going to have this extra iodide kind of floating around in there. Okay, nope, I apologize. We need 2 of those. I got to balance out my charge. So those 2 iodides are going to bind to that 1 lead. And those are going to fall to the bottom of the container eventually as a solid. Okay, so notice that the potassium ions and the nitrate ions are still free in solution. The lead and the iodide have now been bound together. So we get our solid. All right, so let's break it down into writing an equation, a visual for writing an equation. We don't want to have to draw beakers every time and draw ions in them, so let's look at it from the formula point of view. All right, so here are my original compounds. So I'm showing potassium as blue and iodide as pink, lead is green, and nitrate is yellow. And it's a little more work, but until you get the hang of it, if you've got a bunch of highlighters, it's a good idea to get your highlighters out and actually highlight cation, anion in one set, cation and anion in the other. Because what they're going to do is basically partner swap. Sounds a little weird, but we've got a cation here and a cation here, and then an anion here and an anion here. Cations and anions are going to swap. So lead is going to swap its nitrate for iodide. Potassium is going to swap its iodide for nitrate. So here's my 2 new potential products. Either one of those could be insoluble. Okay. Now, if the potentially insoluble products, the products that I make, are both soluble, then I get no reaction, and I can just stop there. But if one, or it could even be both, we could produce 2 solids in solution, but if at least one of those things creates an insoluble product, then we have a precipitation reaction. Something is going to precipitate out of that solution. And by the way, the abbreviation we tend to use for precipitation is PPT. So if you see PPT, that's what we're talking about. So in the case we're looking at, the lead iodide is what is insoluble, falls out to the bottom right here. So there's our solid, everything else is aqueous in solution. So we can write the equation as shown here. The lead iodide would be the solid, the potassium nitrate, there's our solid, potassium nitrate is aqueous. All right, so that is a look at solubility patterns and how to predict the products of a precipitation reaction. We want to now take that information and look at how to represent that equation in its ionic form. So what we want to do is boil it down to the essence of what is happening. We want to take out the things that aren't really reacting. They start as aqueous and end as aqueous. And that's what we'll look at in section 7.